about three-phase transformer connections. I just realized. All right. This is an overview of three-phase transformer connections. We've talked about this already, but we need to go over it again. We know that there are Y delta, delta delta, delta Y, and YY connections. And we've already talked about how those affect the calculations. I want to emphasize once again that the important part is when you do calculations, as much as possible, you want to stay in phase. When you only have line coming into something, then you have to look at the line and find the phase from that information, okay? So when we work these things, we want to remember that we want to work towards looking at phase calculations. Okay. And we remember that line current in a delta is square root of 3 times the phase current, and the voltages are all equal. Remember that Singer uses the V symbol instead of the E for voltage. I'm used to looking at E, and it always makes me shudder to look at the V. It should be easy because, you know, voltage is voltage. So it ought to be easy, but phase voltage is equal to line voltage in a delta. Why? We have the voltages are different. The phase voltage is square root of 3 times the phase voltage gives you the line voltage. The line current and the phase current are equal. Okay? The considerations used in the selection of the connection type is grounding. Generally speaking, when you have a delta system, unless you have grounded it some way, it's an ungrounded system. Y is almost always a grounded system. The center point will always be a grounded point. All right? And I've talked before about some cities supply Y power, some cities supply delta power, or the utilities in those cities. Like the city of Los Angeles supplies a delta supply. It's ungrounded, and theoretically it has no potential to ground, but if you see one of those wires bouncing around on the earth, throwing arcs and sparks, you notice that it never ever disconnects because there's no path back to the transformer, so there's no way to trip the transformer unless it touches hot to hot. Unless there's a dead short, an ungrounded system will not turn itself off. If it's shorting to ground, it will just arc weld. Okay? Don't be part of that arc welding circuit. You want to stay out of that system. All right, so a Y, in a lot of people's opinion, sometimes even mine, a Y is grounded and is somewhat safer because if it hits the ground, the hot conductor hits the ground, if it creates a high enough current short to ground, it will trip the breaker because it does have a potential to ground. I'm on that. Okay. In a step-down application, which is most of the systems that we see, it can be Y delta or delta Y, depending on especially dependent upon what you have in your local area. Most users are going to want a Y supply off their secondary coming to their building because they can get three-phase out of that, but they can also get single-phase out of that. So a 12208 is kind of a handy supply voltage if you're running a place where you have to have single-phase loads and you have some motors and it's kind of an equally balanced load. So you have to look at what you want, but when someone is selecting the connection system, they're going to look at what kind of load is it. If it's an all motor load with just a couple little very, very, very few single-phase loads, it'll probably wind up being delta because you don't have a neutral wire running around. Okay. Also, we have open delta systems. Utilities generally speaking, only have an open delta system when they have a transformer blow up, and it will still supply a great deal of the power that it was supplying before without failing. Balanced three-phase loads, which is kind of what we want to look at mostly, is where we have about the same amount of power load in the primary and the secondary. And it's kind of important in a delta load because you can't load one transformer more than the other. In a delta, you really need to have a balanced load. So if it's mostly motors, that's going to be a balanced load. Okay, we started having a couple of questions. Find the voltage across each primary coil, et cetera, et cetera. When you're reviewing this at home, make sure that you look at all these questions and try to answer them. We're not going to go over all of them right now. If you're given a voltage, what is LPR? Line primary, current, 10 amps, no. I don't remember what they said that symbol was. Let's go back a little bit. I know I saw that. All right, let's go back to our fourth slide or our third slide, whatever it may be, where it was talking about the ideal transformer. And we have our formula here, and it's talking about the number of windings in the primary is equal to the number of turns over the number of turns in the secondary is equal to the voltage in the primary over the voltage in the secondary, which is inversely proportional to the current ratio, which becomes the current in the secondary over the current in the primary. So we see that the number of windings and the voltage ratios are directly proportional. NP over NS is equal to EP over ES. So it's directly proportional, but it's inversely proportional to the current ratio because voltage times current gives us power. And primary power at a higher voltage and a certain current with a lower voltage is going to have a higher current. We can see that, right? Okay. Let's go back to our other slide we were at. Oh, wait. Stopped it completely. Okay, let me do that again. One more time. Okay, so with the ideal transformer, which is what we generally kind of consider, we have a winding ratio is equal to the voltage ratio and is inversely proportional to the current ratio. So the number of windings in the primary over the number of windings in the secondary is directly proportional to or equal to the primary voltage over the secondary voltage. And that is inversely proportional to the current. So the current in the secondary over the current in the primary is the same fraction. So that's an inverse proportion. All right, let's go back to our slide where we're looking at a couple things. And we were going to find a couple things in this particular formula where all right, I want to make a note. They say a step down or a step up may be Y delta or delta Y, depending on whether it's stepping up or stepping down, which is just not true. The primary is whatever the local utility is serving, period. And whether they're stepping down, the customer is probably going to want Y, so it's either going to be a delta Y or possibly a YY. YY, they say, is used very seldom, and that's partially true, but that's because most utilities serve a delta. The nice thing about a delta system is, we've talked about that before, if you lose a transformer or you take one out of service, it will still work. And I wanted to point out that the open delta is also known as a V connection because if you turn the V sideways, it looks like this. And you kind of have a V connection. And because that's how it's wired. So that's why it's called a V connection. It's kind of a misnomer because it should be called a sideways V connection. But you get the picture. Okay, so let's go back down to our calculations we were going to do. I believe we were doing this one right here. And we had to look up the fact what Singer's talking about with this alpha, and that apparently is the ratio. So since the ratio is 10, that means it must be a 10 to 1. Therefore, oh, there we go, the voltage ratio. All right, it's 2400 to 10. Since our line primary voltage is 2400 volts, that is the 1, and our 10 would be below that, so we would wind up with a 240 output because of the 10 to 1 ratio. All right? Everybody okay with that? So if you see this, they mean it's a 10 to 1 windings ratio. So I believe. And so if we have a voltage ratio where we have a primary voltage of 2400, I did that backwards, didn't I? It's 10 to 1. It's a step down. So if we've got 2400 in the primary, our voltage in the secondary would be 240. It tells us a primary power. No, it tells us a current. So we have a secondary current, and our formula, let's put our formula up here. I know this is kind of an inconvenient place, but the number of windings in the primary over the number in the secondary is equal to the voltage in the primary over the voltage in the secondary, equal to the current in the secondary over the current in the primary. I don't like the way that it was written in that other slide anyway, so I'm glad we got a chance to write this. So we have 10 to 1 here. We have 10 to 1 here. And that's equal to 2400 over 240. You can see that that's a 10 to 1 ratio, right? So the current, since this is the secondary, is going to be a 10 to 1 ratio, but in reverse, it's going to be 1/10 of the current will be on the primary. Okay? So our current in our secondary, what does that say? It's 200 amps. I think that says current line secondary. Okay? Over current in the primary. And we can see that this is going to be 1/10 of this, so our current should be 20 amps, right? Would anybody go with that?
Yep.
Is that correct?
So.
Why does it say, oh, it's getting the kVA on the primary. This kVA right here is coming from the primary, I believe. So we have 240 times 200. I take 240 times 200 is equal to 2400 times IP, right? If we cross multiply, I think that's what they're doing. So we get 48 kVA, and I guess we were told that this is 80% efficient somewhere. I didn't see that. that's okay. So we have 38.4 kW. 0.400 times 2. I think I have this all messed up. Well, let's look at the next slide. And yes, I had one of those ratios reversed. So, no, our current's 20 amps. I'm surprised by that. So I guess I had something correct. I'm just not sure what. Where do we get this 115.5 amps? What is that? Current in the primary? 200. Oh, because it's three-phase power, we have to use the square root of 3. Current, line current divided by square root of 3 will give us phase current. Ah, so our phase current is 115.3 amps. There we go. Okay, that's where that comes up from our primary voltage and our primary current. Our primary current is 115.5 amps. Our primary current is equal to primary current divided by the turns ratio. So we should have 11.6, or actually 11.55 amps in our secondary. No, primary, sorry. That should be our primary current, right? So, let's see. Primary line current is equal to times the, I'm not used to using this alpha, but that's okay. We'll get used to that too, I guess. So our kVA per transformer is 27.7 kVA because it's 240 times 115.5. Those are line totals, phase totals. Those are line totals. 240 times 115, those are line totals. Because we've got the square root of 3 times line voltage times line current divided by 1,000. Dividing by 1,000 just putting it in proper engineering notation. So we know that this is about an 83.1 kVA transformer, and 3 of them put together. No, that's the total total three-phase power. Sorry, 83.1 kVA is the total three-phase power. So, all right. Now we want to look at three-phase circuit connections, and we're going to, as an example, we're going to look at a 4180 delta supply. It's fairly high voltage. You wouldn't normally touch the 4180 because you're not on the line crew. And the line crew is not going to touch the 4180 because that's at 5,000 volts. It'll jump a pretty good arc. So the 277-480 is the only one you might actually measure the voltage at. You would not measure the voltage on the 4180 side. Okay? So we're going to have a 277-480 secondary. And we're going to look at adding a load. Now for simplicity, jump slides on me. For simplicity, we're going to look at a purely resistive load. I drew in the windings just like it was a motor, but for simplicity, we're going to just look at it as a pure resistance for the moment. Because we know that if we look at this as a coil of a transformer, we have to look at the phase angle between the resistance and the X sub L. So I think we did this. I did this problem without that. Okay, knowing that we have 277 secondary phase voltage, we also know that we must look at the line voltages, as this is what goes to the load. 480 volts is what goes down to the load. Since the load is a Y also, we can see that we convert back to the phase voltage at the load. So we're going to go down here. We're going to say that we have, what was it, 25, a resistance of 11.08 ohms. And we're going to say that it's a pure resistance just to keep it really, really simple. We know that that's not normally the case with a motor. So these must be some kind of loads other than the motor, but this is just an example, so we just want to keep it nice and simple. So if we have a resistance of 11.08 ohms across each phase, we can see that we'll have a phase current of 25 amps. Can everybody see that? Okay. 277 divided by 11.08, because if it's 480 across the line on a Y, we know the voltage across there is going to be 277. If we have 277 and 11.08 ohms of resistance, then we'll have 25 amps of current flow across each phase. You can see that each line is going to be probably about 50 amps of line current, because it's a series circuit, right? And we have both of these windings as part of the A, B circuit. All right. So now let's go to the next thing. Now we're looking at, we've got to go back to the primary winding, the secondary windings on the line. So we need now to convert back to line totals. So if we look at 480, the current in a Y is all the same, right? Interesting. So 25 ohms at 480 is our line total, right? And what kind of output do we have on our transformer? We have a Y. You can see where all of the neutrals are tied together. They should be taken over here and grounded, because all these windings are tied together on that side. So our phase is A phase, B phase, C phase, and we can see that since the secondary is the same as the primary, the secondary of the transformer is the same as the load, the connection is the same, we can see that we're going to have the same voltage across the phases, so we're going to expect to see about 25 amps across the secondary windings. We're going to convert back to phase, so we can look at just the phase of the winding. We know that we've got 277 volts here, and we have 25 amps of current flow there, right? Because we know that as soon as we convert back to our phases, we're going to have the same as we did down in the phase of the load, because it's YY. So if we have 277 at 25 amps, our primary voltage is what? Our primary is a delta. Our primary is a delta. So if we have 4180, do we have 4180? We have 4180 on our primary winding. Let's go back and look at this. Oh, I lost my, by going to the next slide, I lost my little red and blue stuff. Okay, so I have 4180 on the primary winding up here. And I have 277 down here. Now, power is power, so we have 25 amps down here. So we know that we have 277 times 25, and dividing both sides by 41 gives us 1.855 amps. Now I want you to notice that if we have 4180 at 1.855, I take it back, 1.855. We multiply 1.855 times 4180, we'll get the same number we do if we multiply 277 times 25, because power in is power out, because we're looking at this as more or less an ideal transformer. So now we want to look at now can we see the current in a single phase of a delta supply? We probably cannot see that. So we want to find the line current, because we have the phase current. If we have the phase in a delta, we multiply that times square root of 3 and we'll find our line current. Is that correct? Okay. So our phase is 1.855. We're going to multiply that times the square root of 3. We'll wind up with 2.451 amps on our primary line, which we can probably measure. Okay. We're going to talk about open delta just a little bit. Just to remind you, I know that you've read this and you're familiar with it, and that an open delta should be able to handle about 2/3 of the power of the closed delta system, but it will only be able to handle 58% rather than the 66.66% that we think it should. The primary of a delta-delta transformer rated at 240 kVA and 2,000 volts. Oh, we're going to do this little quiz. We're not going to do this quiz, so if while you're looking this at home, look this over, go to the next slide after you've figured everything out, and you'll find your answers right there. And the rest of the answers are right there. So, I believe that's the end of this little presentation, and thank you very much for viewing. Oh, shit. It is recording? Oh, good. Pardon the OS.